وعلى آله وصحبه أجمعين. This is the third discrete probability distribution we are going to talk about in this course, which is the hypergeometric distribution. If you remember, we studied binomial probability distribution. And if you remember, the probability of a success in one trial must be the same as the probability of a success in any other trial in the binomial distribution, and the trials has to be independent. Also, in the Poisson distribution, the independence is a condition and it must be there. So independence was a condition in both of these two distributions. Now, what if we deal with populations that are very small or small, fairly small, and the sampling is without replacement? If you remember, if the sampling is with replacement, it would be a binomial because the independence would be guaranteed in that case. But if we sample without replacement, then the condition of independence will not hold. So in this case, when the population is small, population size, and the sampling without replacement, we cannot use the binomial or the Poisson. So we need another distribution, and that's the hypergeometric distribution. So when do we use the hypergeometric distribution? We use it when the population size is small and sampling without replacement. Put this in your mind. What are the values of x? Well, x in this case would be the number of successes as usual, but this time in the sample. And the sample size is small n, okay? So we have a population of certain size, size capital N. And in this population, we have two groups, okay? Let us say the group or the event of success or the group of success that we are talking about in the question. And the number of elements in this group is capital X, okay? So we can say that capital X number of successes in the population. And the other group, the number of elements in the other group, of course, it would be capital N minus capital X. So, for example, let us look to this example. We have here 3 light bulbs were selected from 10. Of the 10, there were 4 defectives. So we have in the population 10 bulbs. 4 of them are defectives. If he is asking what's the probability that 2 of the selected are defective, so defective is success in this question. So 4 would be capital X. And capital N would be 10. And either the items are defective or good. We have 4 defectives and the total number is 10. So there are 6 good bulbs. How did we find 6? Capital N minus capital X. So capital N is 10, capital X is 4, and capital N minus capital X is 6. This is the situation in the population. And now we will select a sample, okay? From this population, we will select a sample of 3 bulbs. So the sample size is 3, okay? So we have capital N, the population size, capital X, the number of successes in the population, and capital N minus capital X, number of failures in the population. And then we have the sample size. We select a sample of size N. And this sample could contain some elements from here and some elements from here. So number of successes in the sample is small x, and number of failures in the sample is small n minus small x. How to find the probability of small x? Okay, probability of number of successes in the sample. Capital N minus capital X, you choose from it n minus x, and capital X you choose small x, and capital N you choose small n. So in general, how do we find the probability? How did we define the probability before? If you remember, the probability is defined to be number of elements, okay, in the event over the number of elements in the sample space. So how can we talk about the sample space here of this experiment? What is this experiment in general? It is selecting, we are selecting 3 bulbs out of 10. So that's the sample space. Each trial, you will have 3 bulbs, 3 bulbs, 3 bulbs, okay? 3 bulbs are selected from 10. So in how many ways can you select 3 from 10? The combination 10C3 will give you the number of ways in which you can select 3 out of 10. So this is the total number of elements in the sample space. Now, what is your experiment? You need to select these 3 bulbs from good bulbs and defective bulbs. So what do you want to do? In this example, I want to select 2 defectives, out of the 3. Okay. So you start by selecting 2 of the 3 defectives. In how many ways can you select 2 of the 3 defectives? Well, 3C2 will give you the number of ways. Times, because the second step now, and, so and always multiplication, and you need to select the last one because you are selecting 3. Don't forget, you are selecting 3. So you chose 2 out of the 3 defectives, and you need to select the third one out of the 6 good bulbs. So in how many ways can you select 1 good from the 6 good bulbs? 6C1, and this will give you the answer. So you can use the calculator 3 and use shift division to write 3C2, then multiply times 6C1, and you divide that by 10C3, and the answer would be 0.15. So this is the probability of selecting 2. This is the probability of 2, by the way, probability of 2 defectives. So probability of 2 defectives. This is the probability of selecting 2 defectives of the 3. So again, we have 10 in total, and these 10, this is not correct. This is not 3, this is 4, because these 10 are divided into 4 defectives and 6 non-defectives, or 6 good. So these 10 are divided into 4 plus 6. So if you add 4 plus 6, you should get 10. So if you have seen like what I did, 3 plus 6 is 9, this is 10, you immediately notice there is a problem and you correct the mistake. So 10 is 4 plus 6, 4 defectives, 6 non-defectives. And 3, the sample you are going to choose, 2 of them should be here, defectives, 1 of them is here. So 1 plus 2 is always 3, 4 plus 6 is always 10. If you look to the formula, if you add small n minus x with plus x, you will get small n. And if you add capital N minus capital X with capital X, you will get capital N. So that's the definition or the formula we use to find the probabilities in the hypergeometric distributions. Another example, a company has 20 employees, of which 8 have college degrees. So these 20 employees are the numbers in the population, capital N. And they are divided into college degrees, so C, for example, let us say C college degrees. How many with college degrees? 8. So if 8 of them have college degrees, then 20 minus 8, okay, this is capital X, 20 minus 8, which is 12, this is capital N minus capital X, would be the one with no college degree, okay? This is college degree, this is, for example, false, okay? No college degrees. Good. Now, according to the company owner, 3 employees were recently selected at random. So this is the sample we are going to select. So small n is 3, okay? We will select a sample of this population and the sample size is 3. Suppose all 3 of those selected did not had a college degree. What is the probability of this happening by chance? Yani, what is the probability of selecting 3 with no college degree? So probability of 3 no college degree. Okay, so C, C, C. Here in the denominator, in total, how many employees? 20. And in total, how many you are selecting? The sample size, 3. So this is you put here. Now here, these 20 are divided into 2 groups, 8 college degrees, 12 no college degrees. And these 3 are divided into, in this case, you need all of them did not hold. So you need to choose all of them from here, and you will choose 0 from here. 8C0 is 1, by the way. So you can just divide 12C3 by 20C3, and the answer is 11 over 57 or 0.193. So that's the probability. So what is the probability of this happening by chance? That's the probability of this happening by chance. About 20%, 19%. And when you select the 3, all of them had no college degree. Another example, a population of 10 items. So this is what? Capital N. Contains 3 that are red. If we say that red is success, so this would be capital X, and green is capital N minus X, the green, the 7 green. What is the probability that in a random sample of 3, so this is small n, 3 items selected without replacement, this immediately tells you that this is a hypergeometric distribution. We need to select 2 red and 1 green. So what is the probability of selecting 2 red and 1 green? Okay, in total, how many items we have? Capital 10. How many in the sample size? 3. We will select 3. Okay, these 10 are divided into 3 red and 7 green. And these 3 you need to select. You need 2 red and 1 green. And you can use the calculator to find the answer. Another example, capital N is 10, capital X is 7, small n is 4. Let me mention something here. Now, the number of items that you can select, for example, let us talk here. Now, if small n is 4, small n is 4. So what would be X number of successes in the sample? Small x. Small x in this question could be 0, 1, 2, 3, or 4. It cannot exceed 4 because n is small n is 4. So what is the probability that x equals 3? Let us find out. Again, C, C, C. In total, we have 10, capital N, and small n is 4. So we are selecting 4 out of 10. Those 10 are divided into 7 and 10 minus 7, 3. And those 4 now I need to select how many of them? 3. Can I select 3 out of them from the 7? Yes. And in this way, you are going to select 1 from here. 3 plus 1 is 4, so everything is fine. And you can find this probability, 7C3 times 3C1, which is 3, by the way, over 10C4. So the answer is half. So probability of x equals to 3 is half. What is probability of x equals to 5? Can x be 5? In fact, I cannot select 5 from 4. Okay, the sample size is 4. The sample size is 4. I cannot select 5 from the 4. So x has to be less than 4 always, or at most it should be 4. It could be 4. So here this probability is just 0. I cannot select 5 out of 4. Okay, what about probability of x greater than or equal to 4? Well, I cannot select 5. So this would be probability of just 4, because probability of 4, there is no more than 4. So what is probability of 4? I have 10, 4, and 7, 3. And now I need to select 4 out of this 4. And all of them from the 7, from the success. So here I have to select 0. Now if you find this probability, we said 3C0 is 1, so you can cancel, it is 1, and you can divide 7C4 by 10C4, and the answer is 1 over 6, or approximately 0.17. So this is the probability of 4. Of course, he can ask a question like this. For example, find the probability distribution. Construct the probability distribution of this example. And then to construct the probability distribution, you need to find, you need to write all the possible values of small x, and you can use the formula to find the probability of each one of them. This is the probability distribution in this case. One other point I needed to say, assume, for example, in this question, that small n is 8. Okay, that I'm going to select 8 from the 10. All right. Now, what are the possible values of x? If n is 8 in this question, what are the possible values of x? X is number of successes from the sample, from n. So I can choose, in fact, 0, 1, 2, 3, up to 7. Why up to 7? Because I have only 7 successes, and small x is the number of successes. So put in your mind that the values of x depends on small n and capital X. It is, in fact, you can say that x is the minimum. X in general, let me write it here. Small x is 0, 1, up to t. Okay, let us say up to c. Let us call it d, up to d, where d is the minimum of capital X and small n. D is the minimum of capital X and small n. So if here small n is 4, then it cannot exceed 4. If n is greater than 7, then it cannot exceed 7. So you have to consider the minimum of small n and capital X. Another example, another part, find the largest x bar. We have seen a question like this in the Poisson distribution. Find the largest x bar, prime, so that probability of x greater than x prime is greater than 0.25. Okay, we need the largest. We have x from 0 to 4. Okay, I can start from 4. What is the probability that x is greater than 4? Greater than 4, 0. X cannot be greater than 4. 0 is not greater than 0.25. So this is not good. Okay, 4 is not the answer. This is not greater than 0.25. All right. Let me try 3. Probability of x greater than 3. Greater than 3 means probability of 4 only. And probability of 4 we have just found 0.17. And 0.17 is not greater than 0.25. So 3 is not x prime. What about probability of x greater than 2? Greater than 2 means probability of 3 plus probability of 4. We have seen that probability of 3 is 0.5 and probability of 4 is 0.17. So its probability, it's 0.67. And this is greater than 0.25. So the largest x prime that satisfies this condition is 2. 2 is the largest x prime. Now, if we extend the definition of the hypergeometric distributions to more than 2 possible outcomes, k possible outcomes, 3 outcomes, 4 outcomes per one trial. So this will mean that we will have the population divided into more than 2 groups, 3 groups, 4 groups. So when you select something, it's not necessarily green or red. No, it could be 3 colors, 4 colors, 5 colors. So how can we find the probability in this case? In fact, it is just an extension of the formula. You add here how many groups you have. You multiply by the number of groups. So let us immediately consider an example. Consider a situation in which a used car lot contains 5 Fords, 4 General Motors, and 5 Toyotas. So here in this car lot, we have 3 different, not 2. So if you select a car, there is no 2 outcomes, 3 outcomes in this case. Fords, and there are 5 cars, General Motors, and we have 4 of them, and Toyota, and we have 5 of them. So in general, capital N is what? 5 plus 5 plus 4, 14. We have 14 cars in general in the population. All right. What do you want to select? 5 cars are selected. So the sample size, the small n is 5. Okay. 5 cars are selected at random to be placed on a special sale. What is the probability that 3 are Fords, 3 Fords, and 2 General Motors? Okay, as always, see here now you have 3 different models of cars, brands. You write C, C, C. The total number of cars is 14, and you are selecting 5 in general, the sample size. So this is capital N, this is small n. Now these 14 are divided into 5 Fords, 4 GMs, and 5 Toyotas. Okay, how would you like to divide these 5? I need 3 of them are Fords, 2 of them GMs, and that's it. 3 plus 2 is 5, so you select 0 from here, and you can find the answer by the calculator. One last example, Bacon's Hill Trees and Shrubs currently has an inventory of 10 fruit trees. So in the inventory, they have 10 fruit trees, 8 pine trees, and 14 maple trees. So this is the inventory, and it's divided into 3 kinds of trees. Fruits, there are 10. Pine trees, we have 8. Maple trees, we have 14 maple trees. So in general, inside the inventory in the population, how many trees we have? 18 plus 14, 32. So 32 trees in general. Okay, it plans to give 4 trees away at next Saturday's Lawn and Garden show in the city park. 4 winners. So we need to select 4 out of the inventory, 4 trees. So small n is 4. Okay, 4 winners can select which type of tree they want. Assume they select randomly. What is the probability that all 4 winners will select the same type of tree? Well, the same type of tree means F or P or M, and or means plus. So you need to find the probability that 4 trees selected are fruits plus the probability that 4 trees selected are pine trees plus the probability that 4 trees selected are maple trees. Well, probability that the 4 are fruits, as usual, we have C and we have 3 kinds of trees. So C times C times C. In total, we have 32, and we are selecting 4 of them. And these 32 are divided into 10, 8, 14. And now I choose all the 4 from the 10. So this is the probability of 4 fruits. Probability of 4 pine trees would be the same, but we are selecting the 4 from here, from the pine trees. Probability of 4 choosing 4 maple trees would be selecting the 4 from the maple trees. So 10C0, 8C0, and 14C4. And in general, we are selecting 4 out of 32. Of course, please, you need to find the answer at the exam. You don't leave it like this. What is the probability that 3 winners will select pine trees? So we need to select 3 pine, and the other 3 will be maple, and 1 maple. All right, we have 32, and we are selecting 4. And these 32 are divided into 10, 8, 14. Now, what do you want? No fruit, okay. 3 pine, 1 maple, and you find the answer. Finally, what is the probability that no fruit, 0 fruit, and 2 of each of the others? So 2 maple and 2 pine trees. So in general, 32, we are selecting 4. Those 32 are divided into 8, 18, 14, 0 from here, 2 from here, 2 from here. This is the end of the hypergeometric distribution. And by this, we finished section 5. If you have any questions.